Hello, everyone. This is Group 7 for presenting the Lab 3 Road Ripper technical presentation. My name is Eurico Costa, and I'm the only member in Group 7. The purpose of this lab is to use the logic available to create a reliable and cost-effective device to implement the brake lights and turn signals with a digital system for the Road Ripper Motor Company. As part of this lab, we are to design and implement a digital circuit consisting of 4 inputs and 4 outputs and successfully derive the appropriate Boolean equation from a provided truth table using Boolean algebra and K-maps as a result of the K-maps and the truth table. And we are to implement the circuit using AND, OR, and NOT gates, and then implement the same circuit using a read-only memory. And these are the provided truth tables and the functional specifications for the circuit. From the truth table, we can create Carnot maps for each of the turn signals and brake lights, as we can see in this slide. With these maps, we can find the reduced Boolean equations for each of the lights, with left front equal to LC and left back equals to SL naught or LC or SR. The right front equals to RC, and the right back equals to RC SR naught or RC or SL. These are the equations we can use. These are the full equations we can use from the truth table. As we apply the laws and theorems of the Boolean algebra to verify our K-map solutions, we come up with the reduced equations. We can now implement them into circuits. As we can see here, now that I have my simplified Boolean equations, I can now implement them using the AND, or NOT gates. I do this first because I am familiar with these gates, and it allows me to get a good idea of how the circuit runs before implementing it with a ROM or a lookup table circuit. It is also fairly easy to read it this way. I have 2 NOT gates, 6 2-input AND gates, and 2 3-input OR gates. The first AND gate combines left and clock, so LC, which is my equation for the left front light, and as you can see, I have it connected there. I also have it connected to the first OR gate. Stop and right are combined in my second AND gate, and my third AND gate combines stop and inverted left. These also connect to my first OR gate, giving me the equation for the left backlight, which is LC or SR. My fourth, fifth, and sixth AND gates are connected to the second OR gate for my right back equation, which is RC or SL or SR naught. The fourth AND gate combines right and clock, so RC, which, as you can see, is the equation for the right front light. With the logical circuit created from my reduced Boolean equations, it is much easier to build the same circuit using a read-only memory, or ROM, also known as a lookup table, or LUT for short. I have the 4 inputs connecting to a splitter, combining the 4 1-bit inputs into a single 4 bits input, which the ROM uses as an address. We know from previous learning that a 4-bit number can have 16 possible values, which is why we can see 16 cells inside the ROM. Each of these cells is filled with a hexadecimal number, which corresponds to a number between 0 and 15. As the inputs change, the address changes, and the table looks at the cell that corresponds to that address. The value inside that cell is then converted back to a 4-bit binary number, which is our output with the most significant bit in the wire marked with number 3, so the 4th bit. We can see that while it is not applicable to every circuit, sometimes using a ROM can result in a cleaner circuit and simpler to read. As you can see, we can use the techniques that we are familiar with, like truth tables, Carnot maps, and digital circuits to design ROM or a lookup table as it's known. Each address of the lookup table corresponds to a set of inputs in this truth table and is used to store the corresponding outputs. The outputs of the truth table are then stored in each of the corresponding addresses in hexadecimal form. For example, in one of the lines in the truth table provided, in the combination stop equals 0, left equals 1, right equals 1, clock equals 1, the result is a binary combination corresponding to 111 in binary, which then corresponds to F in hexadecimal, which is then converted back into binary as the output of the ROM and corresponds exactly to the same digital circuit that I have put together. This concludes my presentation, and if you have any questions, please feel free to post them in the discussion board. Thank you.